Okay. Let's see. All right. Anyone have a patent they want to share out that looks interesting? It doesn't have to be their favorite yet. Last class I shared out that my favorite patent was the resistor by Otis Boykin. He didn't invent like the idea of resistive theory, but he did come up with the packaging around the breadboard resistor that allows people to play with electronic components modularly. So I think that's cool, given that resistors are one of the first three components you learn about in electronics. Yeah. Anyone else have a favorite patent?
I found one for the mocha espresso machine.
The espresso machine?
Yeah. Like the mocha one where the water is in the bottom, then as it boils, it passes through the coffee and condenses and then separates.
Really?
And the original design was designed in the 1950s
Uh-huh.
after the Second World War, and it hasn't changed since.
Oh my gosh. I
They'll
think,
still use the same design.
I recently saw a paper. It was like in the physical review letters. People are trying to optimize the pouring of pour over coffee.
Yeah.
Because the challenge of coffee is like when you have coffee grounds, what you need to do is you need water to pass over every single ground um uh to extract every single flavor, but you don't want to over extract. So how do you like pour it from what height and what rate, laminar or turbulent, to like ruffle up the coffee grounds and like actually let the water pass through? Imagine like if you pour too quickly or like or pours all through, you don't get the grounds at the side. If you do too slowly, then it over seeps. So yeah, it's actually a complicated problem. And as you can tell, scientists enjoy coffee a little too much to be thinking about this. But you could probably imagine what kind of other areas in chemical engineering or processes it might have. If you think about like particulates, flowing water, and extraction. Yeah. Yeah. Cool. Thanks for sharing, Enrico. Anyone else want to share their favorite patent? Yeah. You have your least favorite. Can I like come closer so that it picks up on the mic?
I don't think this is made. I don't think this drives the overall price of EpiPens, but I think EpiPens, like the drug epinephrine, actually isn't that expensive, which makes me think it's just the patent that drives up the hikes up the costs.
Yes.
So I
Yeah.
think that's unfortunate.
Yeah, the idea of like again patents, it's an interesting topic to talk about. Like how do you give credit for someone and like their money and financial credit and also like intellectual credit to someone, but also make it accessible. I think Manu at some point we'll talk about open source later on in the class and different forms of licensing. Maybe someone's a bigger history buff here, but like I think it was like Tesla who didn't patent AC or like something, some form of electricity so that everyone could use it. But as you can tell, like it's been really messed up for like industry and infrastructure if he like decided to do something greedy. But I think he didn't really get that much acknowledgement, even though he did a very good thing, which is a little sad. But I think that's why it's important to acknowledge people and like at the very least for the efforts that they do open source it. Okay. Anyone else? Anyone from online have a patent they want to share out?
So it's not one of my favorites, but like I like the patent. So there is this particular lens, so which can generate electricity or energy when you blink. So it's a contact lens. It has got piezoelectric materials around it. And when you
Oh,
blink, it can generate electricity. And
so
that
just
can,
like mechanical forces
yeah,
okay.
yeah. So depending on the blinking frequency and all, they have to modify what kind of piezoelectric materials, what the shape should be. That part is there, and after that it can be used for ionophores. Like there can be some drug depot in the that contact lens, and from the general electricity now it can act as a like force to push the drugs which are like charged towards the eye.
Oh, okay. I was like, oh, I don't think I'd blink enough to charge my phone, but you're saying it generates like enough charge on it such that it can help the delivery of charged drugs?
Yeah, so like that's the idea which it was. So there's already patent on that, where they have already made this contact lens
Yeah,
which can generate energy when you blink.
that's awesome. Can you post that in the Discord?
Yeah, I will.
Connected to something, or only once you take it out and remove it from your eye, then you get the energy that it stores?
I think the drug delivery is in the eye itself, right?
Yeah, it's iontophoresis, and they want to do iontophoresis. I mean, they have not included that in the patent. There are other people who want to do that. That's the main idea behind having a system like that. But it can be like it's a future prospect of that particular thing.
Yeah. Awesome. Anyone else want to share? Yeah.
I tried to find a single patent, but really came up to many of Eppendorf tube, basically the little tubes that you put in small centrifuges for preparing samples and lots of molecular and cell biology work.
Yeah.
Was quickly overwhelmed by the several dozen patents, all of which have a tube that looks almost identical to me, but all of which have claims of being slightly superior over all the other ones based on the shape of the lip on top and how easily you can open it. But here's one, looks like that.
Yeah, that looks very familiar.
Yeah.
I think so one time I heard a talk by what's his name? I'm forgetting. Langer, Professor Langer from MIT. Bob Langer. He has like a lot of patents. So he gave a talk about so there's requirements for what something has to be in order to become a patent. We can talk about that, or you can ask Manu directly, but I think novelty is one of the criteria. And then it's very ambiguous about like what constitutes as novel. It's like, oh, yeah, what do you think constitutes like novel? Because like if you make one tweak to like a bigger thing, is that novel? Yeah, or do you have to do something from scratch? I don't think so, given all these iterations on the Eppendorf tube. So there's some gray areas, but that's kind of why you had to research a lot of patents, because you had to think about what the prior works have been and how your new idea compares. And yeah, cool space to be in. Oops. I'm gonna do not disturb. Okay. Let's see. Ars, I see your hand up.
Yeah, I have a little crazy of a patent to talk about. It was a little wild. Cannot find it right now, but saw it a long time ago. So imagine two cycles being over each other, and sort of you stop cycling and the other cycle starts choking you to some extent. So they named it a death trap. That was long back. It was granted maybe 1900s. I really doubt why it was made in the first place. But yeah.
So wait, it's two cycles that are connected, like wheels, you mean?
Yeah, so sort of a cycle over a cycle so two cycles kept over each other, and then you stop cycling around. So it's the cycle on the top starts choking you, the wheel on the top starts choking you.
So and you don't know the purpose of this? If you can you post that in the Discord? I'm having a hard time visualizing this.
Yeah, so I have a picture of it, but I'm unable to find the patent. Wait, let me just
Okay,
send
yeah,
that.
if you can share the picture, yeah,
Yeah,
thinking.
yeah, that it.
I think somewhere in the patent space there's also this idea of utility, like so I think novelty, utility. There's like a few more criteria I'm forgetting, but yeah, we can look that up. But yeah, I'm very curious about the utility of two cycles. Yeah. Wait. Uncrustable. Oh, the PB&J. Yeah.
So ridiculously detailed because they claim that so the patent is for a sealed crustless sandwich.
Sealed crustless sandwich.
Crustless.
Okay. Yeah.
And it was all fine. They were basically claiming that the difference from prior art is that theirs is long lasting and the filling doesn't act.
Wow.
But then they went around suing a bunch of grocery stores for selling any sandwich that was sealed and like crustless until
sealed
eventually,
and crustless.
yeah, specifically.
Yeah.
Until eventually their
Yeah, that's the spiciness of like patent law. It's like, oh, like how much overlap is there in ideas, and that's why people sue each other all the time. Does anyone know how long a patent lasts? And off the top of your head,
10 years maybe.
yeah, someone said 10 years.
It depends.
Yep.
I think it's 20, right?
I 20 was in the back of my head. I think there's a
Yeah, I think it's 20.
yeah, 20 is, and then like for example, books copyright, that's 70 years, right? So that's why a lot of old books, like I don't know, Origin of Species, that one's like reprinted, and you don't need any like copyright from Charles Darwin or like whoever has the ownership of the copyright.
Characters too.
Okay, book characters, like I guess.
Like I remember like Winnie the Pooh.
Oh.
Just recently, now I can make them like horror movies and you didn't have to worry about this.
Yeah, but there's also a process of renewing, right? I think, like for example, like I don't think Mickey Mouse can be printed on just anything, can it?
I bet not. I bet
Yeah.
they renewed that.
Didn't that recently happen?
What?
Yeah,
I thought the person-
Wait,
Yeah.
with what? With Winnie the Pooh?
that you can use Winnie the,
Winnie the Pooh,
Mouse's
Winnie the Pooh
copyright.
definitely, I guess maybe Mickey Mouse also might have just happened.
Okay, maybe Mickey Mouse too.
and
Okay.
specifically in Paraguay. So,
Why?
because there was a preceding Mickey Mouse before Mickey
Oh,
Mouse.
yeah, wait, here,
playing
show,
copies.
show Winnie
So
the
what
Pooh.
you
Wait,
need
turn
to
this.
do now,
Wait, it's literally called Winnie the Pooh, and it's a horror movie,
Oh
and they're
my
allowed
God.
to use it because
Yeah.
the patent from 75 years prior is now free.
So
Open domain.
what you need to do now is the current year is 2025. You subtract 70, 75 years and think like, what is something that like was a big phenomenon 70, 75 years ago, and then you capitalize on it. So I guess that's like kind of the revival of certain old cultures, which is cool. Yeah, and you can do the same thing with like patents as well, like which patents are expiring soon. I think that'd be some interesting.
EpiPen expires
oh.
2025.
Oh, EpiPen. Okay, great. This is great
Yeah,
news.
just
Like,
reading,
do you know if there's any like biotech companies that are capitalizing on this?
Well, it said like there's generic stuff that's like been kind of competition to keep the epinephrine, the EpiPen like price in check.
Uh-huh.
But hopefully it does a better job.
Okay,
next
okay.
year.
Yeah. Okay, okay.
So if someone files a patent on something, can you buy that patent? Like if I want to replicate their product?
Yeah, I think this involves like you get their permission and then they get a certain fraction in royalties. Again,
Okay.
don't quote me on this. I think
Yeah.
Manu actually has patents. So then he actually knows about it. But I think it's like similar to the idea of licensing, like, oh, I give you permission, but it's always a matter of permission and like royalties. Yeah.
Going back to Tesla, one of the other like biggest mishaps of a patent that I can think of recently is Sriracha.
Oh yes,
They
yes.
missed out on that and missed out on billions of dollars. And now everyone, like the reason why you can see Sriracha, aioli, Sriracha plays at Subway is because they didn't like the actual initial group of Sriracha
Yeah.
didn't capitalize on their own brand.
Yeah.
And so everyone else was able to use it.
Yeah. Yeah.
Okay.
Another spicy one is the whole CRISPR thing.
Oh,
Yeah. So especially in the biotech.
Conversation.
Does anyone know this story? I guess Megan, you were in Michael Jewett's class. This was this like recent that I learned more about the details, but it had to boil down with the difference between like showing CRISPR work in vitro versus actually in a biological system, and like given that you can fast track certain patents as well. So if you fast track it and it gets through first, then you get dibs on it. So again, it's like, wow, like there's so many complicated things about patents. Cool.
And Feng Zheng showed it would work in mammalian cells.
Yes,
With
in
birds,
mammalian
that was
cells.
the whole thing. And then down in Charpentier at Berkeley. That was the whole thing.
Yeah, I think they did prokaryotes only.
Yeah.
Yeah. Okay. Yeah. So again, very exciting field to be in. Cool. Let's see. I think let's see. We'll take one more or a few more. Rupesh, I see your hand up.
Yeah. Am I audible?
Yes, you're audible.
Okay. Yeah. So there are multiple patents I've searched and that interest me. So I'll share about two most I like most. So one is the cathode ray tube. So maybe people have seen the uh, bulky TVs or bulky monitors. So the patent of that. So basically, it works like so. It shoots the electrons to the phosphorus screen, and it brighten up the one point in the display, and that uh, ray shooting ray of electron is controlled by the voltage, electrical voltage. So that's the thing how it works in the CRT TVs. And another patent I would like to share is like insulin production. So like uh, I guess so, using rDNA method, so using the uh, insulin gene from the humans, so eh, we produce the insulin. So the company name Gene Tech, which has patent related to that.
Yeah, no, those
I'll
are
maybe for the
cool.
further reading.
Oh,
Yeah,
yeah,
I'll post it in the Discord. Yeah,
oh,
for
perfect,
the further
perfect.
reading.
Yes,
Yep.
I think when Manu is now here, he's gonna take over and talk about Fred Park. Um,
Did you guys cover some patents?
Yeah.
Sorry, I was stuck in traffic. I just made it. Which all patents you guys?
there was Adrian, right? Aiden, sorry. Aiden talked about his least favorite patent.
Which is the EpiPen? Yes. Uh, that's correct. And so what is it about the EpiPen? In terms of mechanics that makes it that we can circumnavigate that?
It looks like it's just the auto injector in the spring inside, that is so it can deliver precise amounts of drug.
So it's what's the volume? Yeah, we might use the board. What's the total volume that needs to be injected?
Can't
Is there an open source EpiPen out there?
Well, now it is because the patent actually expired.
The patent expired.
Of December.
Yeah, so does that change the price of EpiPen?
I have not looked into it.
Yeah.
I would expect so.
Why don't we hack an EpiPen for fun? So can somebody bring an EpiPen on Friday? How much does it cost? We can destroy it, it should be okay. Should there be some EpiPens and kind of emergency supplies and other things? Let's look into it, otherwise we'll just ask Shyama to buy some. Yeah, it actually would be fun to read a patent. And again, remember, I'm kind of emphasizing the idea of undisciplined. It's good you have that.
Yeah, I think that the acronym looked a little different.
Yeah, I have, this is
Yeah.
my acronym.
Okay. Yeah.
Undisciplined learning has a context where you should have the object in hand, you should have the patent in hand, you should hack around to really say, oh, does this actually make sense? Any other patents that people talked about or want to talk about? Has anybody read the Lego patent? I'm surprised nobody brought up the Lego patent. It's been like, no, nobody's read the Lego patent. Okay, do you guys know why the Lego patent is so famous?
Is it because of press fit?
Yes,
Yeah.
there's a real trick to it. Why was it that Lego is the only company that's really scaled up? I mean, they make just numbers by the numbers, which reminds me, everybody needs to post their by the numbers. Is it on Discord yet?
Yeah, it's a combination of Discord and Notion.
Okay,
Although
that's okay, but I think it would be useful if, so by the numbers, just type in on Google how many plastic pieces, can somebody tell me how many bricks they make?
A year? Or
Yeah,
what, should we guess?
let's guess before do a Google.
How many pieces?
How many plastic pieces does Lego make? Don't press enter yet. How many people think it's a million, a billion, or a trillion? 10 billion?
100 billion.
100 billion.
50 billion.
50 billion. Okay, let me write that down. 50 billion, 1 trillion. Some people said 100
I said
billion.
100 billion.
You said 10 billion?
Yeah.
And Everybody is above 1 billion for sure. Should we put 1 billion? Anybody for 1 billion? Remember, that's one Lego
I
brick.
would say 1 billion.
1 billion.
Wait, we're doing per year.
Per year. Sorry, this is all per year. And I'm talking about total bricks, like we are counting for not kits or sets. Okay, let's press enter.
What's your guess, Kevin?
I think around.
36 billion, less.
100 million a day.
What? A day?
No.
No.
Well, no, it's 100, well, yeah, sorry, I said 100 million. Yeah, 100 million a day.
Okay, okay. So how do you do that? I mean, that talk about scale. That's why I want you to read that patent. There's something very magical in that patent, which is they figured out when you combine two objects, there's this idea of over constraints, and we'll talk about over constraints and under constraints. Every time you put two Lego bricks together, they have a precision and a kind of a tolerance of around 5 microns, which is insane to think about for macroscopic objects, that every time you click, that's why you can stack them up, because errors add sequentially if you add and add and add, and then the other piece will not connect if that error is not bounded. So the big reason that that patent, of course, that patent has expired a long time ago, but they have the precision of molding that nobody else has been able to match in terms of materials and their molding techniques. So if you ever visit a Lego factory, you'll see there's a lot of secret stuff, which is really driven by why they're able to do this. And so a group at MIT measured their precision, and so there's a beautiful paper on it too. Read the patent, and that has to do with the shapes. The shapes cause this kind of a constraint criteria. You want to provide it in a scenario that there's compliance in the system that self-corrects for error to bind to this 5 micron, below 5 micron. Any other patents on undisciplined learning? Yes.
So mine was this like vent. So the reason it's my favorite patent is because my engineering teacher at high school invented it.
That's pretty
It's
cool.
This one-way vent
Yeah.
that allows helium to escape a spacecraft while not letting CO2 enter the spacecraft.
That's pretty cool. Okay, so you're saying helium and CO2 are in the same chamber, and you need to make something that
There's no CO2 in the chamber, but there's CO2 in the atmosphere of, say, Mars.
I see. So CO2 is outside, and you want one-way diode. You want helium to escape, but you don't want CO2 to come in.
Yes.
Okay, I see. So no influx, only outflux for gases. So before you tell us, anybody has an idea, how would we do that? Don't tell us. Give us a fraction of a second. Huh?
Yeah.
Maxwell's demon will do that, by the way. Some of you know that joke, no?
Yeah.
Yeah. Read about Maxwell's demons. This will take you in another world.
Yes, there's a little guy who controls a door.
That's correct.
Yeah.
But he can see molecules and he can open and close doors. And of course, Maxwell's demon can do that. Okay, was there an idea?
Oh, just by the size, helium is smaller.
Helium is smaller. Yeah, so that's an interesting. So I don't know if some of you guys know this. I think I won't give this as a homework assignment, but a couple years ago, everybody hated it and I loved it. I gave this as a final exam to my stat mech class. It's a undergrad, grad mixed class where for final exam, I had brought helium balloons. Everybody got a helium balloon in the final exam. It was a 3-hour writing exam. And they were supposed to calculate the size of an helium atom. Something to do with the balloon. And it turns out, actually, helium balloons are leaking helium all the time. And it was a polymer physics class, and they knew everything about thinking about how polymers and their thickness determine pore size. So you could go back if you knew the rate of flux of helium. If you could just measure how your helium balloon is losing its weight over time, that is that flux. But in that case, there is also an inward flux. Okay, size is one idea. Anybody else have any other ideas? Yes. Pressure, that's an interesting way of exploring that. And I think one thread that would be is
on Mars, you said?
Right.
Is this in space or?
Yeah, so this would be used on, say,
Aircrafts.
a Mars mission
So this was intended to be used for Mars rovers that use a nuclear generator.
And then what's the patent? How does the patent do it? Tell us the,
Oh, yeah, so.
yeah,
it
and then
uses-
can you make sure you post that patent on Discord itself? Yeah.
So there's this like porous kind of like block, where the pores are like, because it works because helium is such a small molecule.
Yeah. And then you need some back pressure to actually get through the pores.
Actually,
Or it's just totally passive.
I believe it's totally passive
I see.
because of,
I mean,
I'm
there is
looking up.
intrinsically pressure to begin with if there is some
Yeah.
helium in here.
It works
Because at some
through-
point of time, the rate of flux will then decay too much.
How do you make the pores small enough that you can just differentiate between such small objects?
Mhm.
Like CO2 is still really small.
So, anybody? Now we've suddenly moved, and I'm telling you about, this is all a discussion around undisciplined learning. I just want to, there is a philosophical lesson in this. If you care about something, you will think about it. And if you think about it, it doesn't matter whether you have a PhD in material science or not, you will dig into it. One way I know how to make really small pores, I don't think it'll hit the helium, is actually high energy particles. So many high energy particles are used to make nanopores. I mean, all of you know nanopore sequencing, that's a biological pore, but there is a parallel version of solid state pores that essentially use ceramics, and they bombard the ceramics with high energy particles that generate, I think 16 nanometer is the one that I know, that you can easily do something like that. And you get it for free. You just generate a high energy source. Somebody had put some material, and this is ceramics. It's like very hard materials itself. And you get these beautiful pores that are perfectly circular. And then you cannot control their angle though often. So they can be any angle. It's because this particle went through in all kinds of ways. So I could imagine that would be, and this method is scalable because you make trillions and trillions of them at the same time. Zeolites is another space. That's self-assembly based pores, but I don't know if zeolites would work in this. Yes, Frugal. I don't remember. It's clearly not, what are the ones that pass through our body, pass through? It's clearly not neutrinos, but it is one of these particles. And
is it at most 16
no, I think this is a number I remember because I'm looking at a patent recently and I was excited about that they had very precise dimensions, which is very interesting. So natural phenomena is leading. Okay, anybody online? They already somebody shared some sets of patents.
Some shared cathode ray tubes. Another one shared like a contact that uses mechanical like blinking to produce electric charge. And that
triboelectricity.
Yeah, and that charge allows like charged drugs to pass into the eye.
Ooh, that's pretty cool. Okay, so can we all make sure that each one of you at least must share a patent? You know, I casually mention these as homeworks, and I'm not going to check, but this is you're enhancing each other's learning. It's really, really fun when you go down these rabbit holes. So do it, because otherwise it's sort of you don't appreciate the depth, and then you realize that you get into a habit of reading patents. Just have you can have write a 5-line script that randomly posts a patent in your inbox every day for 2 months. And you see, you learn so much because you're not thinking about it. And here is somebody trying to teach you something in the context of problem solving, not in the context of some book, but directly. And you learn, wait a second, how did this person connect this idea to that idea? And, you know, in the old days, it used to be a classic way people would learn. And if you're trying to learn problem solving, it's actually very important to learn from others as case studies. There's also silly patents. You can search for silly patents. I saw Apple just posted one, which is because they know the acceleration of this object so precisely, They posted something that every time a phone falls, first of all, they actually know. Enrico and I were talking about this. The statistics of this is known. I think per year, how many times does a human being drop their phone? Let's guess.
An individual person or?
An individual person with an iPhone, any phone, per year, how many times? 10 times?
20. I drop mine about
50 times? Huh? So you can't use yourself as a base because you might be an outlier.
25.
300, 5,000, 50,000, no. Okay.
That you had to be throwing it on the
Yeah.
ground.
Is it a day or a year, Professor?
Say that again?
Per year.
Per year, yes. How many times you drop your phone? Any guesses? Again, the reason I'm mentioning this is you could do this with the by the numbers tricks. You could kind of think a little bit about, oh, what is the time that people hold their phone in their hand? An enormous time. Yeah. So I think kind of the number that Apple knows this exactly because they record all our data. And so it was of the order, I think 150 or 200 times, which is like almost every other day, which is true. Like small drops, big drops. So the patent was that because you know the accelerations, a drop has a very particular kind of an acceleration signature. And then the plan was a silly patent. They had little drone motors on the side for it to just change the orientation just a little bit. Because you know, impact like this, it can be more resilient to impact like that. It's less resilient. So it's the cat uprighting itself in fall, but with a tiny amount of momentum. Anyway, it's cute. It sort of sets the stage like, oh, that's interesting that technically that could be done. Yes.
I pitched out, but I forget the specifics about what is required for a patent, like novelty, utility, and stuff.
Yeah, I mean, I think we will spend some time not writing patents. I'm not, again, we are a very open source inclined class. When the projects come about and we've sort of realized that, yes, we have something new, we will talk about this and we will explicitly make choices for every single project, whether we put it in an open domain. And this is what's so beautiful about Stanford. Stanford does have, I think, the only university that I know that gives explicit right to inventors to choose and make that decision. Many other places, that decision doesn't fall in your hands. So if you've invented something super useful for the world, remember insulin as it was given out for $1 for everybody to use. It's very ironic that still today insulin is not available. But the original patent was all given out. But Stanford does have that in their clause, which is very important and powerful. And as inventors, we should all be aware of it, utilize it. So we'll have that discussion. But having said that, then there is kind of importance aspects about what do you need to do and share and tell. And reading patents teaches you that, but I'm not referring reading patents in that context as yet. I don't want to teach you guys that. There are plenty of lawyers that get paid pretty well to cover patents. Don't worry about it. What's important is in undisciplined learning, see how people solve problems. And sometimes what's important is if you start with a product that you like and then go read the patent, you might also find nearby patents that other people tried solving that problem and it didn't work so well. And because of that, we were able to, you're able to understand kind of what are the nuances. And sometimes the nuances are in scale. Sometimes you'll find a patent that actually came up with the core idea, but it didn't succeed because the sequential things that came about solved the key problem of scale. So like there's a beautiful series of patents in the railway industry about how to link cars, like trains. Lots of patents were filed on it, but there's the key ones that worked because accidentally leaving a train compartment behind would be a super bad thing. Similarly, brakes. Trains didn't have brakes in the early days. Super scary. So you may or may not stop at a train station. And then came these massive series of patents, and then people had brakes that would then break the linkers, and then the other cars wouldn't brake because people just put the brakes on the engine. And so the person who got it right was really that scaled. And so there's a lot of learning. It's an infinite soup. So try to kind of dive in. It's not a casual thing I've mentioned. It's something important if you really care about learning problem solving. Okay, so we are going to transition into something that I want to talk about today, which I learned in one of my classes at MIT. Kevin took a similar class. This is sort of a philosophy from Alex Slocum. He wrote this book called Precision Machine Design. And we're going to use this framework for not just designing machines, but just to kind of overview of how to think about your projects and kind of lay out a very systematic plan for how to execute on it. So I want to make a list of projects that we'll discuss today if that's relevant. And so you guys have a name for the project? Call it something.
The
fun.
coral one?
Yes.
The one of the touching, it's called Helping Hands experiment.
Okay. Coral Helping Hands. Let's think about a couple others. So has anybody else as yet pitched projects that they're excited about? Again, you don't have to do this project, but this is something that should have bothered you and thinking about it. I'll take maybe 2 from the class here, and then I'll take maybe 2 from online. Putting you on the spot. Go for it.
I have one that's still developing,
Yeah.
but inspired by the Velelas.
Yes,
actually.
yes.
What if we can find a way to have like autonomous small sailboats sailing around the ocean, maybe mapping biodiversity or like cleaning microplastics?
Awesome. So kind of the way that I'll flip is, and I think this often happens, that you have a vague idea of problem space and you get inspired by something, and then it gives you a hint of an idea. And then we will use this framework to kind of consolidate it so that it, rather than being vague, it becomes very specific. And sometimes I'll file ideas as, oh, I care about this principle, it must be useful. Enrico is referring to this massive bloom of Velas that we saw. It's this beautiful jelly zooid that floats around and uses sail, a passive sail. So it's unlike many other jellies, it actually has something sticking out. So feels like for distributed low-cost sensors. So we had talked so much about ocean data needs to scale. The number is we need to scale by 100 to 1,000x in terms of the amount of mapping we need to do. The other inspirational thing about it, it's a material that survives in the ocean for a long enough time. It's not plastic, but it has this chitin, and we collected a lot of them just to analyze that material, for example. I hope you guys saved the adults too, right?
Yeah.
Did we freeze them?
Yes.
Okay, we also find them often enough, and it's well. So there is a notion, but then the way I would anchor is still anchor in the problem. And so then the problem definition would be around autonomous data collection platforms. And then when we get to solutions, we will have one of the solution as these passive sails and think a little bit about the biological context to it. So this is important to anchor and hone in. So one way I could just say this is 100x passive ocean observations. And I'm keeping it vague right now, but you'll see the whole purpose of this framework is we have to narrow it for you to be able to evaluate. That's okay. Okay, I'll take one more. Who else wants? Yes.
Reina and I were talking about maybe doing something climate change.
And Reina is in the class right
Yeah.
but she is not here. Okay, yes.
About doing something climate change and disease related.
Say more. What disease? What?
Basically, the change in infectious diseases, like dengue, for example, as the climate changes in certain countries. And we were thinking of either doing it like self-report or some kind of autonomous data collection.
Yeah, but I want to hone in on the problem. So is that fair to say that high resolution dengue mapping, what would be a problem statement? Like what's missing? What bothers you? Does it bother you that dengue shows up randomly at any place, anytime? What aspect? Yeah.
I think the biggest problem is that it's unpredictable. So maybe the ability to predict where being at.
Yeah. Now, dengue has a very strange periodic cycle, by the way. Like people have been struggling over it. There are some models out there that has this seasonality, but with a cadence that's quite unpredictable. And also, why do new areas have dengue now? So I would kind of say leave dengue surveillance as a. And the reason I'm doing this exercise now is because I want to use this for all the projects. It'll help you hone in to say, this is what I want to do. Okay, so maybe we'll take 2 examples from the class. Anybody wants to chime in? What's been bothering you? Raise your hands, and then I'll also pick people that don't speak that much in the class, and I will do the same. So you might want to be quiet, but I'll make you talk at some point in time. So, okay, so anybody in the class?
Anyone on Zoom?
Raise your hand. I will take, so wait, Devajit, I've read what you wrote, so I'm gonna wait to see if anybody else wants to. The online class is thin today. Anybody else has a project idea that you might want to just hint towards? Because remember, we have to build projects that are collective. And
The mic's up.
I want to make sure that people online and people physically here
So you said, can
are teaming up together. Did anybody raise?
Sarika, it says that their mic isn't working, so they might just type it.
Okay, yeah, go ahead, type it. Okay, Indumita, go ahead. And then introduce yourself itself as, because I don't, yeah. Can you just?
So my name's Indumita. I'm from, I'm doing a master's in biomedical engineering at Imperial College, London.
Yes.
So I've noticed there's not a lot of people from London. And my idea is basically, I haven't really looked into it that much, but I found this paper a couple of years ago about using ultrasound as a way of like creating a virtual lens using ultrasound to focus optical light through tissue. And in this paper, they've done it with, I think, like a medium light tissue, and they proved that it works. And I thought this would be a really cool idea because ultrasound transducers are relatively cheap. So I think this would fit in with the Frugal side.
Yes.
And you can, I'm not sure what diseases this will apply to, but it would be very useful for countries where it's hard like to image underneath the skin or through tissues. So
yeah,
that's
I mean, what I like about this is that it's, although you have an inkling, and again, very similar to the Bella Bella, that you have a seed of an idea, it's valuable to pose the problem. And then the way I would pose the problem is just deep tissue imaging. And I can already tell you a problem that we have worked in Cameroon for some time. And we have been working on, the best way to describe is electromagnetic imaging of onchocerciasis. So onchocerciasis is, and I'm just choosing this, I'll use this as an example for your problem, but then of course we can broaden it out. Onchocerciasis is a terrible parasitic disease, and river blindness is one example of it. So I don't know if you've known this history in Zaire. There used to be this scenario that people were puzzled why so many people go blind when they live close to a river. That's why it was called river blindness. This is millions of people going blind when you live close to a river. And then it turned out there was a black fly that transmits this pathogen. It's a nematode-like parasite, onchocerciasis, that then travels through your body. It lives inside your eyes, and sometimes even in your vision, you'll actually see a parasite go by. It's a really terrible disease. It's been on the decline. There's been a lot of work that's happened. But one challenge is that it lives, the adult lives in nodules. So the bite of a fly, but you know, we get bumps all the time, and the only way to do it is to remove it surgically. So that's called a skin snip removal, but it can be somewhere in very critical parts of your body, and it's very tricky to do a surgery. But before that, you need to know whether the onco is dead or alive. And so what we've been doing is we've been building electromagnetic patches to do kind of an impedance measurement of the skin to tell whether there is tissue that's different from a control group. So the intuition is that although it's biological, it has many sets of materials like chitin on its surface. It protects itself from the rest of the skin, so material properties would be different. So Indu, the reason I'm just mentioning this is I can imagine another alternative approach to this, which would be we need very low cost, but deep tissue imaging on the surface of the skin to identify whether it's worth it to go ahead with the surgery or to just wait because the adult parasite is dead. And you really have to remove many of them. So I'm just choosing a context, but I like, you know, let's just choose as an example for, what I'm trying to do here is I'm trying to steer you all away from, of course, you're excited about one idea, but we're going to generate hundreds of ideas for that problem. And it might still turn out that the idea you're thinking about is the top winner in that space. Like, that's why I had said that I want to not use the word 3D printing ideas. I want to anchor in the problem. This class is all about problems. And then I want you to not, this is a very tough to do, but we all get so excited about our ideas. But if you just take a step back, you can generate a massive number of them as well. And maybe for that particular match, it was not a good match. So we're going to choose deep tissue in the field imaging and kind of for diagnostics, just as a criteria. And then I'm just writing onco here because the onco has a very important disease context. And then this diagnosis is also important because there are certain sets of drugs out there, but people have co-infection with another parasite. So you cannot do mass drug administration because if they have that other parasite, both of the parasites die and their brain goes into this massive immune response and people die. So unlike many other diseases that are parasitic that you say is like, oh, the drug is so cheap, let's give it to everybody. And they started doing that. And then they had to pause the program. That you can't do that without diagnostics, because if you had another infection from another parasite, the combo of it is so deadly that people die. And so you cannot in a community ethically say that, oh, even 0.1% of people that will take that drug will die. That just would not work, even in the disease population. And that sets the backstage. So that's why diagnostics became important.
What's the other parasite?
It's called Loa Loa. And it's a very cute name, but it's a terrible parasite. Okay, we'll take one more problem. I see another person. Arth, go ahead.
Right. So a problem that I am excited about is developing a hemodialysis machine. I
Can
think
you
I've
introduce yourself?
Okay, yeah. So I'm Earth. I'm currently a research assistant at a collaboration between MIT CSAIL and IIT Delhi. A lot of my research work lies in social analysis of air purification. I have a whole lot written about it on the Notion page. But the problem I'm really excited about for this class and in general is creating a hemodialysis machine. From a primary review, what I could find is there has been a lot of work in creating a large machine that's a little cheaper. But nobody has really tried to, or I mean, to the extent which I have explored, I haven't been able to find folks who have been trying to create machines which people can keep at home and maybe do the treatment themselves. I think solving this problem is a little important for three reasons. One is the costs associated with the treatment. It's very expensive, roughly $3,000 to $5,000 every year. Very inaccessible for a lot of people in Asian countries, African countries, on and forth. The second aspect has to be travel limitations. With hemodialysis, you cannot really travel to lots of places just because you have 3 to 5 hospital visits every week. And the third reason is lack of control and a sense of agency over your treatment. So that's really why I'm mostly excited about this problem. A lot of people feel that the treatment is not under their control or they do not have agency over that.
Okay, that's fantastic. And I think one of the important aspects is we are going to do this now but it's valuable to motivate them by explicit sets of numbers. And the assumption is that for sets of problems that you're doing, the first thing you should just do is do by the numbers. Understand the scale of the problem. So I'm already saying, I put this 100x in here already. Now, you could also do a by the numbers to say, oh, what is the budget that we should dedicate to ocean monitoring? And you work backwards from this. Like, oh, not only do I want to scale the total number of measurements made per year, I also want to do that in, okay, what is the right number? Maybe $1 billion. Is that a good number? And then you could say, okay, it can be done. And then you can motivate people around this. We should just be spending $1 billion a year only on monitoring. And so by the numbers is very important. In dengue surveillance, you would run by the numbers. Some of the statistics that's in there, but can you identify the gaps that exist by the numbers in these sets of problems? So everybody's done, I'm assuming, at least one by the numbers, right? Yes. It may or may not have been the problem that you're excited about, but now we have to do that for certain sets of problems that you're actually excited about. So as we're developing our projects, the first thing that you would do is to build by the numbers around each one of those. Deep tissue, and I think these numbers will become very valuable in the framework that we'll talk about today. Because say if I say deep tissue, you want to put certain sets of an intuition around what does deep really mean? And you might say, oh, for the problem in onco, the numbers that I care about is 5-10 millimeters. You're pushing the limit, but you're not going completely crazy that you say, oh, MRI is the only solution that will win. So it sets quantitatively the scale of what you're trying to do. And at that same time, in a hemodialysis context, you would run some numbers about how many cells per minute, like how long should a treatment take? I mean, ideally right now, the treatment might be say 2 hours, 3 hours, sit down. Cost would obviously be in the place, but understanding the scale of the problem by the numbers would become very important. Okay, so we're going to choose 4 or 5 of these. And, in today's class, we can't go through all of them, but I'm going to now draw this little table. Just erase this. And again, it's not perfect. You can modify this framework as much as you want. You can add a lot to it as well, but I at least want all of you to make this table next time when we meet on Monday. So the first thing is really functional requirements. And this forces your hands to explicitly say, what do I really want to create? And we'll think a little bit about this in a second, but we want to be as descriptive, and we'll choose a few examples to do this. Next one, from what I remember, is design parameters, analysis, risk countermeasures. Did I get that right, Kevin?
I think for the most part, yes.
Yeah. Did I miss any of them? That's the most important thing.
And now references.
Yes.
Yeah.
Where was the references?
There's a double R. Yeah.
References, risks, countermeasures. But did I get the functional requirement and design?
Yeah, exactly. Those are the first 2.
So you can start seeing that the farther you're going along, and we will do this for multiple ideas so that you have some metric to compare and say why your dream idea may or may not work. So it's not just functional requirements always remain the same, but here you get to list as broad sets of ideas as possible. Then we kind of go and become explicitly really analytical. And if you can get to this part of the project as quickly as possible, this is really where all the math, this is where whether what you have dreamed is a pipe dream or is that even real? Does laws of physics allow you to, and can you prove that? Like when I had said, oh, I'm going to make pores out of some high energy particle, that might sound like a pipe dream, but it might also be true. that turns out to be true. So how do you actually prove early enough so you haven't sunk all your time and resources? So we're going to get very analytical in here. This is simulations. This is any compute resources, any numerical things, any experiments that you can start doing explicitly. Then we want to list sets of references. This is to back up your by the numbers, because when we are evaluating things in a team, you want people to feel that they have sets of resources in place. Here is the explicit sets of risks, things you know already that you're worried about, and you can start accounting for them. And then there is countermeasures, which is how do you handle that risk? And certain sets of ideas would have. So, you know, again, this is very, I find it useful. I explicitly do this for all of my frugal science projects that I take on seriously. It might feel too formal. I don't like many of these design templates and other sets of things. This one I do like because it keeps me honest. It's one place. I want to onboard somebody on the project, you immediately pass them on, they can start adding to it. It's kind of your reference library you can always going back to. So I have hated most design advice often because I feel like I want to be free. I want to just think out loud, and all that is great, but you want something to actually counteract your creativity to keep you grounded. And so this is one template that I've enjoyed. There's many like this. People have their own sets of ideas. I've also liked Alex's use of it in many ways. So it's sort of, it stuck with me. So I passed that along. I'm not saying this is the only way to do it, but at the least we will do this. You can also do other types of things in the class. Okay, so let's choose now, and we're going to start with, let's start with the coral because we've discussed it a couple of times. It's well developed at this point. I know Danny and then Debbie. Is Debbie online?
No, Debbie.
Not today. Okay. Is Debbie?
Yes, I'm online. Sorry.
Awesome. Okay. Debbie, are you local or no? Where are you?
I'm local, but on Wednesdays I have a second class I have to rush to. Hence, usually I tune in on Zoom if that's okay.
No, it's fine as long as you're there, and it was important that you're there today, so it's good. Okay. Anybody else?
We've got a third person also that I know is interested on Zoom.
Yes. So that's good. I think just we'll kind of chime in. But by the way, the FRDPARRC and everybody is working on everybody's project. So we're going to start coming up with ideas. And this is why it's useful to do this collectively, that you're not, whatever you're working on is fine, but we will massively populate this. So everybody is welcome to chime in. I just want to, so from a functional requirements point of view, what are our functional requirements now? So imagine you've sort of started reading about it. You have some vague ideas. You've done by the numbers, which you've done already for something like this. Let's ask ourselves, what would be the critical functional requirements? And then of course you guys should chime in, but anybody can chime in for what we have heard so far. So what would be the, say, some of the most important functional requirements?
Like,
yeah, like what do we want when you
say,
when you say this was a success? What needs to happen for you to believe that you achieved the goal you wanted to achieve? So one functional requirement could be is reviving a bleached coral, right? But now that's a little vague, right? Yeah. So we're going to now go narrower. So we say revive bleached coral. And the reason I'm saying that revive is, you know, what does that mean? At the least it should live for some time. So what's the point? At least for a year, right? I mean, something along the science. So I want to start anchoring physiological things here. So you might say that this, what we mean by this is 1 year. And now you might say coral is, that's too broad. There is so many types of corals. Is it really good to start with that? And then I might cross that to say Acropora. I mean, I don't know, whichever one, choose your evil, but it's useful to anchor. And then when you're working on dengue, we'll modify the functional requirement to not do a global thing because we don't have capacity. We start with like, oh, in Brazil, in this particular place, this would be our good functional requirement. Because then you can anchor yourself to one context. It might be that it turns out some species are easier than others. Some species are more sensitive to it than others. So we care about choosing. And it's not that you're not letting go of your dream, but you're also realizing that when you're starting something, it's important to anchor. Okay, so we've done, say, revive, 1 year, a bleach coral.
Like
yes.
Reintroducing symbionts, reintroducing the symbionts.
By reintroducing symbionts.
Yes.
So then suddenly we have narrowed that. And I think one of the kind of factors would be is in this sort of sets the stage for the problem. And between this and this, there is a little bit of a play, because we might say that the purpose of this is really lots of other people have already been thinking about reviving coral. Maybe we don't care about every methodology. We are going to freeze ourselves. That introduction of symbionts is the one that we believe. You know, you might realize that, oh, introduction of symbionts is a broad term. These might be, so in design parameters, we might end up choosing, maybe these are genetically modified symbionts. Maybe these are totally artificial or new symbionts that are still natural. So you can expand on those sets of ideas. So depending on what I'm trying to say is, if you put it in here, this doesn't change. If you put in here, you can choose many strategies and you may or may not end up using it. So it's a little bit, if you tighten your functional requirements a little too much, you end up in this situation, then you're going on that track. It's fair if you have thought quite a lot about it, because then there is a flavor. You built the team around that skill, for example. And you're like, what is novel about it? It's like, this is the skill we have, so we want to explore this much more explicitly. While you might be in a stage where you haven't built a team, and it doesn't matter so much, you're happy going many which way. And it's also, a field might be crowded. Then you say, you know, I don't want to step on these other sets of things. If they find a solution that's great, it's not going to be kind of what I want to invest time on. Okay, so any other functional requirements? Let's think out loud. It's frugal science, so cost has to be there. Yes.
The time scale at which you
do it. So first of all, it's like a dying, or it's like CPR, or this is emergency services. So if you arrive too late, you're done. So in some sense, there has to be a time window. It might be possible that this solution ends up being a two-step solution of some kind, that some of those corals, that something is done quickly and then something is done over time. So in that respect, let's think a little bit about what would be we should put some constraint around time, and we should put some constraint around cost. So first of all, this would arrive from your by the numbers. I'm just going to put, what's the right intuitive number to put? So we said size of Germany, 80% of that bleaches. How much money do you think we can put if we were to say we could revive all of that coral, like per year? I like the number billion. Okay, $1 billion, right? Whatever that number is. Yeah. Do the numbers, but get a sense for what is attributable, and then it might turn out how many coral heads are there in total, and based on that, you might arrive at a number. It's, if you just have absolutely no idea, then you can start in one place, still put something and realize, no, that was unrealistic. I'll put $1 per, you know, I can imagine getting every human being or small portion of human beings on the planet to say, you adopt that coral. That particular coral is yours and you pay $1 per year. That sounds reasonable. I think something like that could be done. So this number doesn't sound too bad to me. If I was to say a campaign was to be built around saving coral for the next generation, would people be willing to pay? And I think this has happened in conservation before, so it has past situations around. So I don't know. It's worth thinking about. But this would come from by the numbers. For right now, we'll just toss something in here because I just want to not spend too much time on this. But time is a critical one. So what have you all learned? How quickly does a bleach coral die in the field?
There's a lot of factors that.
Yes. So let's toss them out and we might come upon something.
The factors are the different time frames.
let's start with factors and then we'll choose something about time frame because it'll constrain our problem of urgency in this problem.
Yeah.
Like just order of magnitude. Do we have 15 days from an event of a massive bleach? Do we have a month? Do we have
I would say it's
weeks?
Weeks, anywhere from 3 to 6.
Okay, I like that. And right now you can also put something in functional requirements a little bit vague. The more work you do, this can get refined and further. Oh, you realize that's the species I was working in. You had to do some step 1, step 2 type of a process. So already in my head, when I'm thinking about step 1 and step 2, you know, when an emergency services arrives, they first stabilize a patient and then they do something. So now we've moved to design parameter. So another kind of a scenario would be is that it's a 2-step process. And then suddenly it has a fork in the road that there is repair, but there is stabilization. Another sort of a thread would be is it's a 1-step process. And so suddenly now I could strike these sets out, but it feels right to me to at least give ourselves a little runway. Like the first thing you do is to what? And ask ourselves a question when there are no symbions, why do they die? Right? What's the most critical? So do we know the answer? Yeah,
There's
what's
a few,
the stress?
but
Yeah.
the biggest one is they lose their nutrients.
Okay, so food is the biggest one to begin with. What are the other ones?
They can very quickly get overgrown by other algae when they don't have the symbiont.
Yeah, but that comes from antibiotic, or the coral is producing something that's making it not enabling other algae to attach, right? So that would be antibiotics or something like that. And then I can immediately see that the stabilization effect is actually a pretty cool one, because you might think about this as a critical criteria for. So now you are really in your idea phase. And here you want to be a little bit uninhibited. It's okay to just think as wild as you can. So you don't want to judge because many of these other things will put you in check. So here, it's not just your favorite idea. So like one idea that we came up with last time was, oh, if we had trapped symbions in hydrogel droplets, which is kind of what I'm excited about, but there would be many other ways to do this. And then you give latency and you give much more contact time. It actually turns out with coral surfaces, there is all of this beautiful flow that occurs on the surface of coral. I don't know if some of you have seen those videos. So coral surfaces have cilia, and they use it to both generate mucus, they use it to actually move bacteria around, so we could exploit that. That implies that something that can attach to the coral surface can actually be self-distributed. So Roman Stalker had this beautiful paper when you look at coral, and people have not really understood. It's a little bit fractal, but around there are these beautiful eddies that occur because of miniature cilia. Oh,
I think someone sneezed.
okay. Sneeze is okay. Actually, sneezes occur. Why do we sneeze? Do we know that? Exactly. It has to do with the cilia. Because sneeze occurs that because the mucus has built up so much that cilia cannot pump. So a pressure effect in place. And the very first behavior from a context of animals, from an evolutionary point, is a sneeze. Because sponges sneeze. This is a digression. Okay, so cilia. So the point I'm trying to make is, let's list through it when you throw, and we won't go into detail of every one of them. You want to throw every possible thing here. So, you know, one of the contexts around this would be is if it's natural symbions, if it's modified symbions, and you can already see that it makes a lot more sense to categorize it.
Yep.
Because I would break this down into delivery mechanism, the actual payload of what you are delivering, and also thinking a lot more about, so the payload and the delivery might sort of change. So this is really a payload section. You must, by sticking to this, you must have one of these payloads. By sticking to these sets of approaches, you must choose the delivery vehicle. And there might be another criteria. What do we want to apply here? There's something big that's missing in our design parameters that would be useful. Yes.
Well, wait, I don't know if it's something that's missing, but
Yeah,
if you think for
add
the two-step
more,
process.
Yes.
If you like the symbionts or the payload, that's the long term.
Yes.
But what if you had maybe hydrogels is a great one,
Yeah.
but what if you
Give some
introduce food,
skin. Yeah.
immediate food to keep it
Yeah.
alive,
Stabilize.
stabilize it, give it the small.
Yeah. I mean, I think I'm thinking antibiotics is kind of another way. If we do believe that algae grow, that's a super easy one because it's very critical. You can see it very clearly, the sets of species that take on. There's a lot of interesting mucus biology. Now mucus can be synthesized. Maybe their capacity to synthesize that mucus goes down and that has the antibiotic properties. So you can think of many classes of mucins. And what you want to do is add, so that we will later on subtract. And it's also possible that that might suddenly explode the scope of your project. But then you say, no, for the first phase, we're going to focus on this part. That's also okay, because that gives you a visibility. And we say, oh, we're going to focus on the delivery vehicle for phase 1, because if we don't have that, then we don't even have this. Or you might say the other way around. I think we can get to stabilization, but the first thing to really do is let's focus on the payload, because if we don't have that, there is no long-term survival. And that's also a fair remark. Sometimes problems cannot be split that way. Sometimes you cannot break them because all of them are so intertwined. I mean, many social problems, actually, one thing that we chose everything to be two in kind of we will choose something where we will focus on the social context of the functional requirements. Now, another design parameter for saying cost is to bring down to that cost. And there's a type of a solution where you say, oh, this is a solution that a community member, any local conservation community member can come and go treat this. Or is it, the techno world of this would be is coral saving robots coming down, powered by ChatGPT, whatever. So that's another vision of the world. And, lots of people are actually doing in seagrass restoration. There's a lot of robotics that's being introduced. I'm not denying that it's not a good idea, because we're also talking about a massive amount of area. So this is sort of the delivery process, but there is a second, we can call that platform. That platform could be humans, that platforms could be robotics, surface robots. But there is still something important that's missing. In a problem like this, I would want to include, which is measurement. And this is a key problem sometimes that we often miss, because it might be that this key criteria is what gives you all the feedback. And you say, oh, I need an imaging system on coral over a long period of time. How many of you have seen the documentary film Chasing Coral? Nobody? Okay, another homework assignment. Watch Chasing Coral. Super cool movie. What I remember from that movie was that they had a hard time catching the moment of the bleach, because it happens at any moment. And they had put all these camera equipment underground. They get overgrown, so they got no footage. Like the moment they wanted to catch bleaching event to show people what it feels like, so they would deploy these. There's anticipation, and it didn't happen. But then places that it happened, by the time you arrive there, the whole thing is bleached. They wanted to catch the time lapse. And then in the end, I think they got some. They had to engineer around, but that means measurements. So in some fact, at the least, if you're making a perturbation on something, you need measurement technologies, and you need to lower the cost of that measurement because it has to scale. So there's a whole bunch that's already been done in this space with ROVs, lots of underwater ROVs are around, and it'll set you as a stage for saying, oh, I'm thinking about measurements early on, because it'll tell you cost will include measurement cost per se. Now you can look at all of this and might say, oh, this number is hard because I am accounting for many other things to make that happen. But then you might come about with scale. So it's important to have, you can have a dialogue between these two things. But if you don't start with this, then you miss the point. Like you are not able to anchor a project in. So there's too much flexibility. You can do anything you want. So there has to be an anchor. How are we doing on time?
11:46.
Okay, I'm gonna do this quickly and then choose one more project actually. Okay, so what could we do on the analysis side? What can we do today? What types of experiments would we do to initiate to say that whether the strategy works or not? The first one is something that you've already started thinking about, is you actually just put some damn symbionts on. You take a coral piece, you bleach it. You need very systematic ways of bleaching something so that you don't cause too much stress. It's as close to a natural, so you need an experimental system. So the first thing you start doing is building an experimental context around this. You have a bleaching protocol, and then you ask whether what does symbiont uptake even look like. And this is hard because the moment you do that, everything else might change. But it's important to have some anchor point, something quick that you feel, and it might be somebody else's results. In analysis, they are not all your results too. Somebody else might have worked on this idea that, oh, they saw, like what we have seen in our data set is we can get coral larvae to take symbionts. Now, if we understood that better, potentially that it implies that, oh, maybe adults can also take that. What tissue, what did the exact time scale of this look like? So in this analysis, the most important part is I want this to be very quantitative. So anything that you do, so it would imply from this that an answer might come out that the contact time between a symbiont for a coral to identify what species it is, it to make the decision and somehow harass the symbiont to come in and be engulfed to live inside this home again is at the least 15 minutes, 15 hours, whatever that number is.
Yeah.
Because it sets the stage to say, oh, I need to make sure that my delivery. So when I say analytical, what should come out of it is some key anchor point that is as quantitative as possible. Yes.
Would it be important to see if, for example, we talked about the fork of stabilize, like if you bleach and then see if food or antibiotic would even extend it. So maybe that's not.
No, that would be another key thing that has to be done, which is kind of you start with the baseline on stabilize. This was for uptake, and you do another one for stabilize. You do the same class of an experiment and ask yourself a question, whether what does that actually look like? I think the idea is that this is an extension of this, except much more granular. Like, for example, any material, oh, that material has to survive in the ocean for some time. So I just take seawater, I take a whole bunch of material, I toss them out, you put in hydrogel, it totally disappears immediately. Or you want that property to exist, so you measure, you're starting to do material testing. And so then one person in the team really is focusing on this to say, oh, no matter whatever happens out here, we will have a material. Now it's really tricky. You might argue that the moment you put something on the coral, you're actually harming the coral.
Yes. That's
right? Because we have cilia and we have flows, and that's why I was excited about droplets. That it might be that you're not coating the damn thing with something, you're just actually putting tiny little drops of this. So only the contact surface is where the symbiont was. Yes.
Also with the uptake, the thing that we've shown right now is it's from a healthy coral to a bleached coral. And then the question is, the actual extendable one is, do you need, what components of the healthy coral are possibly also giving it to bleached coral, or is it just a symbiont? And that's probably the next big question. Do we actually need a healthy coral with all of its symbionts?
But the way I would think is, oh, maybe this trapped object that has the symbiont has some cues, and they might be just small molecules, for example. So that's another experiment that can be done. And I think this one is a tough one, that there is so much unknown biology. So all my analytical things are turning out to be go do the experiment. And that's hard. There are many projects in which you can do the math and you can figure out whether what you had as an idea. Here, you can't do the math because a biological system has so many unknowns in an uncharacterized way. And although there is a lot of literature in many of these sets of things, there is also, so you can see by trend, this is starting to look like a lot of experiments. But on the other hand, in other sets of projects, that might not be the case. You might be able to very quickly rule out things if you just did the right kind of simulation, if you just did like, for imaging, for example, I'm gonna mix and match some of the other ones because you could figure out very quickly whether this ultrasonic focusing on light is actually good for onchocerciasis, because there was a requirement, I said 10 millimeters. So you could do something much more analytical just rather than, oh, I'm going to go do an experiment. Okay. All of this is pretty intuitive, references. You want to teach and train. Some people in your team will be experts in a given field. Others will be completely new. So you want to make sure that you're actually including the kind of references that brings them on board. But I'm going to ask you to defend your FRDPARRCs. And the defense would come from, oh, I remember reading this paper that taught me this framework and I'm tying to it. So, this is why this is important to make that. And then this grows over time, but it's also very directly focused on what makes you defend your sets of ideas. Risks. Let's list some risks in this. There's many risks here. What could we list as risks and how do they help us narrow this down? Yes.
You're introducing potentially.
And what was your name again?
Megan.
Megan, yes.
Like you're potentially introducing non-native bacteria.
Huge risk. Yes, non-native. Okay. Go ahead. Sorry, I cut you off. Yeah.
Which is like maybe different coral have different symbiotes in different areas. You don't know that you're introducing something that's not ever been in that area before and could potentially take over.
Mm-hmm. So one important aspect around this is thinking. The big factor is, of course, some of these are modified if they are modified, or the other way around is let's just stay with the native, which was in there. But understanding that we are perturbing an ecosystem at that time. And so what could a countermeasure to that be? What would you want to feel comfortable, or what would you do? First of all, we should have some monitoring scheme back again here. So we stick a planktoscope here or something that is also looking at symbiont biodiversity and other algae biodiversity. So there is a monitoring program built in the broader area. The other type of a countermeasure is don't do it in the field. Do it in semi-field settings. So semi-field settings are an idea, which is, when you release or you're building a research program around mosquitoes, you don't start releasing mosquitoes everywhere. When the dengue control project happened, they said, we're going to control dengue by releasing more mosquitoes. Everybody said, that sounds crazy. If you just tell it to an average person, that totally sounds crazy. They had a brilliant idea of Wolbachia as a symbiont in mosquitoes to control dengue. Now it's the biggest dengue control program out there. It's called Dengue No More. But that's primarily driven by control. They did massive number of what are called semi-field settings. The lab is obvious, but another countermeasure is semi-field. Another type of a countermeasure around this is how do you build consensus? So now we are getting into the scenario of, oh, maybe we made a mistake. We didn't in the functional requirement choose a location because it would be very different if you were doing this in Cuba versus Palau versus Florida, right? The regulations are very different. So maybe in functional requirements, let's not do this for all species. Let's also not actually do this everywhere. Maybe it's ethically not right to just jump in somewhere and at a place where there are other sets of factors that have played out, where the risks are way too high, where the ocean has not been industrialized in a manner, where there are other cultural norms that might be broken. So I might say, choose a place, just choose Palau, or there's a big relationship between Stanford and Palau, but maybe that's not Palau, it could be somebody else. You might choose a place where the problem is the biggest, just say Australia. And it might be that, oh, Australia has an interesting history of ecological changes, mostly bad. You guys know the famous frog story? Yeah, cane toads. So anyway, so that gives you, I'm remembering something from here and say, oh, for it to make sense, I should add the functional requirement. Okay, any other risk And then I want to just choose one more project quickly. Yes.
You've already kind of nailed it, but the trouble is, how do you have material on anything that's entirely living? Like, it's not just a tree, trees all living, like there's polyps on every part of the coral, and how do you not kill those polyps while applying?
Yeah. And I think kind of now I'm getting a little bit technical, but one thing that I've been thinking about since we spoke is, there is one stabilization. There is an idea that there is a coat which is mucins and much more applying a drug, say antibiotic. But then to introduce the coral, it shouldn't be a big thread. It should really be that, oh, they are spitting in. So the total contact area that you have changed. The rest of the coral is, so the length scales have to match in this problem. So this is kind of why I'm excited about problems, because I could imagine that they can sit and there's also a shear boundary here because of flow. So whatever you put that's in this boundary region will actually stay. Everything that's outside kind of goes away. You need a tagging technique. You need lots of ways of, say, marking your controls, because so then, I could imagine ways and forms that you want to protect this particular one from other predators and fish. That's kind of probably another thing to think a little bit about. But it's important, do no harm. That's an important principle in medical science. So what if some corals do actually come back on their own? And we go out and we're like, oh, we're going to do this. And you suppress its own capability of what it was going to do. And this is valuable. So this is why controls are important. But there is something in the functional requirements. And in many medical projects, you can say that if you're working on a global health project, if you're working on a medical procedure, you have to put a risk criteria to say that you cannot take a step backward, that your solution doesn't cause more harm than, so do no harm is a general thing to apply for all projects, but this is sort of an important. Okay, so everybody has an intuition, so you all feel that you can do this? Yes, no? Yes. Let's okay, I think we're about time. I'm gonna let you all do this as homework. When is a good time? And I think this is a very serious homework, because this you have to spend time on this, because if we don't do this, we won't be able to form teams. So I'll let you choose. When do we want to discuss FRDPARRC?
Should they form teams and then make?
I think it's worth forming teams. It's not a final commitment, but do this exercise in teams that you start learning to work with each other. I want to see everybody's name on at least 2 FRDPARRCs. So do it collectively. You can first do a skeleton, circulate it around. Anybody else can add a little more to it. And it can then allow us like, oh, I really want to work. And then, yes, it coalesces into teams. But you can also just do this as an exercise. Like, I mean, we just spent an hour and less than an hour. And much of this is intuitive, but it is a good exercise for your brain where you feel that so choose one problem that you really want to work on and choose something that you feel is so foreign to you that you would have never thought about it. This is a good criteria to apply. But this is also applies for everybody online. Now, the question is, this I want to put a real deadline on. And we will sit down and print them all out and read and mark them through and kind of see if you're thinking deeply enough. So I'll let you guys throw some deadlines. When do we want to do that? Wednesday, next week? Is that too soon? That's like 7 days. That's plenty time.
Get 7 FRDPARRCs out.
All right.
No.
All right, let's do Wednesday. And we will freeze teams on Friday next week. It's important because otherwise we are halfway point already. So it becomes very important that we do that. Okay, so the big assignment, and this is sort of your key moment in the class that now it's become a contact sport. So everybody, now is the time to self-assemble. Go to the idea page, find out a whole bunch of things. This is also your recruitment tool. Somebody might see this and say, oh, this is so exciting, and I have a skill that I can fill. suddenly this is a great way, because then you kind of see a broader picture. But then you can also do a FRDPARRC around another idea that you were excited about, and in the act of making a FRDPARRC, you might realize that that was the key approach that you liked. This is the problem space that you like. There's many ways to finding what bothers you. I think it's also important to kind of do these sets of teams that are intermingled. And I think we will have a little chat, Kevin, on with the international group, because one thing I want to just make sure is the numbers have fluctuated. And so this would be a time to just catch up with that group in some sense to say who's actually joining teams. There might be some people that have been listening in, but are not as yet committed. So I'm hoping that we have a core group, because remember, if you are listed in a team, then you're part of that team. Like then there's no backing off, because then it disbalances the teams per se. Any questions on this before we disperse? I don't know what I was thinking. We will do 4 or 5 of these, but I think you get. Yes, go ahead.
Yeah, it's a bit of a tangential question, but I just wanted to know what is this Teach Me Anything session, which were supposed to be on Fridays. Could you tell me more?
Friday? Did we put something on Friday? Friday, I was planning to show you guys some optics and kind of some microscopes, which will be key part. So we'll bring 2 of the microscopes this Friday. This Friday, Teach Me Anything is on me. And we will bring a planktoscope and run a demo for it, which Enrico will run. So that's great. And then we will bring an octopi and we'll run a demo for it. And anybody who wants to be diagnosed for malaria will run a test on them. No, we'll run a test on me. Legally, we're not allowed to take blood, but I can donate blood. And Kevin will run an octopi. Okay? Yeah, we can ping Pranav actually to bring one of the latest units. So tomorrow, Friday is fixed. It's going to be optics and optic solutions, so that you all feel a hands-on experience. And the reason I want to make sure we do that is for some of these platforms and solutions that already exist, you should now dive in a greater detail, because modules from that might be viable for something that you want to do. But then line up all the other Teach Me Anything. What are the wacky Teach Me Anythings that have come about?
The Teach Me page is on Notion.
Yeah.
I didn't see any sign up.
Did anybody have any idea? They want to, yes.
Professor, I have one.
Go ahead.
So it's about like decoding fractals. It's about Ashoka Jali and Ashoka logo. So we can have a workshop where people try to decode the pattern. I don't know how helpful it is, but
be fantastic. So something like coding, decoding, like cryptography type coding in a physical.
yes,
Okay.
like a pattern, geometrical pattern.
Yeah, I know exactly what you're talking about. Post a little description of it.
Sure, Professor. I'll do that.
Ragat, go ahead. Everything. Yeah, fill the whole thing, just because these things might determine. So I made it look like it's a linear process. It's not. We came here and then we modified that. So you are like going in loops over and over again, many, many times, because there might be a risk you identify that completely removes a strategy. Perfectly fair. Just keep it listed, but you're doing it iteratively so you feel comfortable that, okay, I've thought about this. I think I have a viable plan. Right? I think that's one of the goals. Okay, any last minute question? Now this is open mic. Otherwise, we're going to call it a day.
You can post any questions on Discord as well.
Yes, okay. I think one comment just for the people online.